actually go, right? They're right up here. They're in row 6 or period 6, period 7, right through here. So they actually belong to the transition metals, right? All these guys are transition metals. What are these called? Alkaline earth metals. Alkali metals. What about the next to last column over here? Halogens, good. What charge do halogens like to form? -1. What charge do noble gases like to form? They don't. What about the alkali metals? +1. They're on the first group. So group 1, +1. Group 2, alkaline earth metals, +2. What about iron? So? We don't know. All right? You can't just predict it. You have to look and see what it's bonded with. I'll show you how to do that later. It was a trick. Okay? What about zinc? 2. It's a 2 positive. What about silver? A +1. What about cadmium? Okay, what about indium? Indium right here, number 49. +3. What about aluminum?
3.
How'd I get that?
I have no idea.
What did I tell you? We outlined these, didn't we? I told you to, in addition to what we've talked about, draw the boot right here, Zn, Cd, and Ag. Box them in. This was a 2 and a 2 positive, both of these, and this was a 1 positive. I also told you to box around these 3, aluminum, gallium, and indium. These 3 right here form a 3 positive. Okay? So make sure you take note of that if you didn't. Okay, what did I say about carbon? Anybody remember? Is it a -4? Is it a +4? Doesn't really matter because the goal is to 8, right? So it's sort of in between. It goes both ways. So as such, it's very versatile. Notice that silicon was like it. Okay? These guys that are touching, except for aluminum, these guys that touch the stair step, what do we call those? Metalloids. And these guys? Non-metals. And everybody to the left? Metals. Okay, what is the atomic number of nitrogen? What does that mean? 7 protons. What, in a charged neutral sodium atom, how many electrons are there in a charged neutral sodium atom? 11. How do you reach that? Okay, with that, can the number of protons ever change in an atom? No. What happens if you have a different number of protons? It's a different atom. So in this case, if I ask you about sodium, how many electrons does a charged neutral sodium have? That means that charges have to balance out. You know that it has 11 protons. It has to by definition. That's what makes it sodium. So in order to balance out 11 protons, you have to have 11 electrons. What about a bromide ion? It comes from bromine. It's when bromine gains a negative charge. It becomes 1 negative. How many electrons would a bromide ion have? 36 electrons, because it had 35 protons. In order to be 1 negative, it had to have an extra electron. Okay? What about calcium? Well, let's know, magnesium. Magnesium likes to form what charge? +2. How many electrons would a magnesium atom, or a magnesium ion, with the charge 2 positive, how many electrons would that magnesium ion have? It would have 10 electrons. The reason? There has to be a negative, there has to be a surplus of 2 positives when you put this all together. There are 12 protons, which means 12 positives. If you know the total charge is a 2 positive, that must mean there's 2 less electrons, so there has to be 10 electrons in a magnesium ion. Okay? All right. You're doing good then. You'll be fine. Now let's fast forward through a bunch of slides. So a charged atom is called what? An ion. What if it's negatively charged? What do we call it? Anion. Positively charged. Good. What are the columns called on the periodic table? Groups. All right. Now, let's look at this. We don't have very far to go today, so whenever we're done, we're done. So you don't have to stay awake for very long in class today, most of you. You should be able to make the whole time, both eyes open this time. Okay, it says, for this example, determine the number of protons and electrons in an ion. You just did this. So let's do it again. Here we go. Question is, find the number of protons and electrons in the calcium ion. What's the first thing I'm probably going to want to do? Okay, find calcium. Some of us are skipping way ahead. Some of us just need to be lucky and find calcium before we do anything else. So let's find calcium on the periodic table. What do you know? What group would it fall under? Group 2, which is called, what they're called what? Alkaline earth metals, and the charge that they have are usually always a positive 2. That's told. Go ahead. It's stated up here, so we're good. Find the number of protons and electrons in the calcium ion. How do you find the number of protons? It's right there. What do we call that number? Atomic number. What is the atomic number for calcium? 20. We have 20 protons. Slow down. Hit the brakes. Find calcium on your periodic table. It's number 20. That means its atomic number is 20. That means its number of protons in the nucleus of that atom is 20. That would mean, in terms of positive charge, how many positives do you have? 20. Now, keeping that in mind, my question here is, how many electrons are in this calcium ion? Okay, let's reason through this. Before some of us are jumping right in. Others are like, whoa, wait a minute. All right. We have 20 protons. That means we have 20 positive charges. What this charge tells you is that there's a surplus of 2 positives. When you weigh out your electrons and your protons, you're heavy in terms of 2 positive charges. Now, we can't manipulate the positive charges. We can't take them away or add them. It's not atom. Get it? Atom. I'm here all semester. We cannot change the number of protons. The only thing that we have to deal with and that we can move around is the number of electrons. So if we're going to get a charge from something, understand the charge is going to come from manipulation of the electrons. Okay, so we have 20 protons, but we know that in this ion, we've got to have a surplus of 2 positives. What's the only way that can happen? If you're stuck with 20 protons, is if you have how many electrons? 18. That's the only way you can have a surplus of 2 positive charges. So that's how you're going to figure this out. What you'll see is on this slide, I left it the way it was, but they make it more complicated than it needs to be. The way you just reason through it in your head is a lot easier. Okay? So you find the number of protons and electrons. That's what we're looking for. So ion symbol, that means you got to find calcium on the table. We figured out that there are 20 protons. Skip all this. Don't worry. If I thought it was important and I thought it would help you, I would go through it, but it's not going to. We've decided that the atomic number is 20. That means there's 20 protons. Now to get the ion charge, that's going to be the difference between your protons and electrons, which is, don't try to memorize that, realize you just did it in your head. You grasp that. You understand how you come up with this charge. It's the difference between your protons and your electrons. So in this case, we had a 2 positive charge and we had 20 protons, so how many electrons must we have had in order to get that? So 18, that's what we already answered. That's a negative charge. So yeah, don't worry about the flow that they just did. Just understand what I just said. Okay. Now, I want to discuss something else that's going to have an impact on some of the numbers that you see on the periodic table. Okay? For example, if you look at, and I mentioned this last lecture, but if you look on the periodic table, let's say, I don't know, what's a good one? Let's look at lithium. Lithium, what is the atomic number of lithium? 3. So how many protons are in this atom? 3. What is the atomic mass of lithium? 6.94. Now, how did we calculate this atomic mass? That's in AMU, we'll say. Okay, that's beyond where I wanted to go, but that's exactly where I'm trying to go, so you're right. For one atom. Let's look at one atom. How do we calculate the atomic weight for one atom? Protons and neutrons together, right? So you've already answered the question, but the question I was going to pose is, why then for lithium is it 6.94? How can you have a fraction or a decimal whenever you're adding together whole numbers of protons and neutrons? And the answer is exactly what she said. It has to do with isotopes. So we have to answer now, what are isotopes? Okay, you maybe even heard it before. You've probably at least heard of like radiocarbon dating, carbon-14 dating and that kind of stuff. This all has to do with isotopes. You can have the same element with atoms that have different masses. You could have a lithium atom and another lithium atom, but they are both lithium by definition because they both have 3 protons, but they could weigh differently. So what must be different about them? A different number of neutrons. That's right, because only protons and neutrons contribute to that mass. So that means that isotopes are going to be 2 atoms that are the same type of atom, but they differ in their number of neutrons, and thus are going to differ in their weight. Make sense? Okay. For example, take chlorine. There are 2 isotopes of chlorine that are found in nature. One has a mass of about 35 AMU. The other has about a mass of about 37 AMU. Now realize that just because there's 2 different types of chlorine that exist doesn't mean they're both 50-50. There's half of each. Au contraire, there's usually there's one that's predominant, and there's one that is, or in this case, not as much of it. And when you see other things, some gases, there are examples of isotopes. There's one form that's very stable that exists in the universe, and only very, very small traces of its isotopes may ever exist. But still, you have to factor that in. And as long as we keep discovering isotopes, these numbers are going to continue to be this way. I mean, they're going to be decimals. They have to reflect what's truly out there in all the different samples that exist. Okay, so take this into consideration here. We say that the observed mass is going to be a weighted average of the weights of all the naturally occurring atoms. Now, in this case, you will see that if you just averaged 35 and 37, add them together, divide by 2, you're not going to get 35.45 as your answer. Okay, so obviously it's not that easy. What you have to do is weight it according to the percentage abundance of each one. So if there's, for example, there's a whole lot more of this than there is this. So that's why this number, when you add them all together and figure in the percentage of each, this number hovers a little more closely to this because there's so much more of it. Okay? I'll show you how to calculate that here in a second. So what you get as the atomic mass of chlorine is 35.45, which should be on your table, or something close to that. Depends on how many decimal points that your table goes to and that kind of stuff. Okay. So what is the difference? How many, well, you tell me. Look at your table. Look at chlorine. How many protons does chlorine have? 17. So in chlorine 35, do your math. In chlorine 35, how many neutrons are there? 18. 17 plus 18 is 35, right? In chlorine 37, how many neutrons are there? There's 20. So see, that's where the mass is different between the two. That's why they're isotopes. Okay. What's nice about isotopes is that they still are the same atom, so they're going to behave the same. They're going to participate in the same chemical reactions. They're going to yield the same types of products. All that's going to be the same. What tends to be different about them sometimes, not all isotopes, but some isotopes are radioactive. In other words, the fact that they have more neutrons in their nucleus it puts them in a place that they're not happy. They're not in their most stable form. So those neutrons sometimes tend to degrade and they start to fall apart. And when they do, they release radiation. And that's what one form of radioactivity is. We can monitor that, and we can find things. Like, for example, like in medicine, you can take treatments with radioactive chemicals to sort of, in small amounts, like for thyroid therapy and things like that, to trace the paths of this stuff through the body and kind of get an idea of where stuff is traveling, where it's being metabolized, where it's getting locked up in the body, and that kind of stuff. Without this radioactive decay, we don't have anything to monitor. They sort of get lost in the sea of all the molecules that are there. But the fact that some of these things can decay and give off radiation, we can monitor it, we can detect it, and follow its path. Okay. Like I said, they have to have the same number of protons, or it's an entirely different element. So they're all going to have different masses. These isotopes are, because of their different number of neutrons. Okay. Take a look at neon. Yes. Yes. Well, I mean, if I have chlorine 35 and chlorine 37, and they're both charged neutral, I mean, yeah, the electrons aren't affected by what the definition of isotope. The only thing that's affected is the number of neutrons. They could, just like two different atoms could, so you could have a chlorine atom here and a chlorine atom here. Whether or not they were the same type of chlorine, it doesn't matter. They could still have two different charges because they behave independently. Sometimes they'll lose. Sometimes they'll gain an electron, and then sometimes they won't need to. Each one has its own independent little life that it lives. So it can do what it wants with its electrons. Take a look at neon, for example. There are 3 isotopes of neon. Notice the percentage abundance. Mostly, what we have out there is what's called neon 20. Neon 20. About 90.48% of all neon is this. Only very, very trace amounts of neon 21 exist. Relatively small amount of neon 22 that exists. I want you to notice the way that these are written up here. This is how we differentiate between the different types of isotopes in terms of how to write them. The easiest way to write them is just the first form, the dash form, neon 20, neon 21, neon 22. But realize what that 20, 21, and 22 means. What does it mean? It's not just the number of protons, and it's not just their number of neutrons. It's actually their entire mass of that atom, the sum of the protons and neutrons. We already know you wouldn't call this neon 10 because all of these would have to be neon 10, right? Because they all have 10 protons. And you don't just call it neon, that neon 10, that neon 11, and that neon 12. That's too ambiguous. You want to incorporate the addition of the protons and the neutrons together in these names. So neon 20 means when I add the protons and neutrons together, it weighs 20. Weighs 21, weighs 22. Another way to write this is the one next to it, where you'll see a superscript and a subscript in front of the symbol. This means what? Right. This is the atomic number of the element in question, and the number above it is the number of protons and neutrons together. So the benefit to this is you can look at on top. This is nice the way this is written right here, because you can look at on top is the total mass. On bottom is the number of protons. All you got to do is it's already set up like a subtraction problem for you to calculate the number of neutrons. 20 minus 10, 10 neutrons. 21 minus 10, 11 neutrons. Mass 22 minus 10 protons, 12 neutrons. Okay? That's the way this works. Questions about this? Okay. So we've got chlorine 35. Back to this example. Chlorine 35 makes up about 3/4 of chlorine atoms in nature, and chlorine 37 makes up the remaining 25%. Now, given that data, how do you come up with this number? Because it says the average atomic mass of chlorine is 35.45. Now, realize that to calculate an average, you have to account for all the atoms that are, and then add them all together and divide by however many of them there are, right, to get an average. Well, that's not physically possible to do. There are so many atoms out there. So what they do is take as many samples as you can to get a good statistical representation of a percentage. Take a bunch of samples and say, I can't give you an exact number because the amounts of each change in whatever setting I'm in, but so far all the data seems to say that every time I take a sample of chlorine, about 75% of that chlorine, whatever the size of the sample is usually always chlorine 35, and about 25% is 37. Chlorine 37. And where this is nice is that we don't have to go out there and count every single atom that exists. We can just take these observations and apply them and come up with a proposed average atomic mass of all the chlorine that's out there. We get 35.45, okay? How? Well, first of all, we know this, right? Our mass number is 35, 17 protons, 18 neutrons. We already determined that. I already showed you how to write this stuff. There's two different ways to write it. This form with this above and below, or just, this is the element symbol, or just the element symbol next to the mass number. So that would be CL35, or you could write CL-35, but that's from another slide, so we don't have to worry about this. I already talked about that. Be able to complete a table like that. Okay, now think about this. Let's break down this table and look and see what it's asking. If I give you calcium-40, you should be able to know all of these things about calcium-40. You should be able to know the atomic number. That's easy, right? You look it up on the periodic table, and you can see that its atomic number is 20. So that means right here in this column, number of protons, that is what the atomic number represents. So you can put a 20 over there. What is the mass number? Well, you can see how this is written, calcium-40. That 40 means that's its mass number by definition. That's how we write isotope symbols. Realize what the mass number represents. It represents what? Sum of protons and neutrons. So that means I know this column over here. Because calcium-40 means its mass number is 40, if I know that the atomic number is 20, which means the protons are 20, I have to have 20 neutrons in order to get 40 when I add them together. So I can fill in that column. I'm only missing one. Number of electrons. Is there a charge associated with this calcium-40? Do you see a positive or negative charge there? No. Then you can assume that it's charge neutral. If it's charge neutral, it has to have the same number of electrons as it does protons. That's where that 20 comes from. Follow me? Okay, let's look at the next one. Carbon-13. What is the atomic number? 6. That means that's our number of protons. So I can put that, these two columns are filled in. What is the mass number? It tells me right there. It's 13. That's the sum of what? Protons and neutrons. So if I know the sum of the protons and neutrons has to equal 13, I already know how many protons I got. That leaves me, I have to have 7 neutrons to get that. Okay? Now, that leaves only number of electrons. Do you see a charge with that? No. So our number of electrons is going to be the same as our number of protons. In this case, 6. Okay? Now the next one is a little bit different. Aluminum-27. You'll see that this one has a charge associated with it. So everything's going to be the same that you just did. Atomic number is 13. If you look up aluminum, that means it has 13 protons. The mass number is 27, as written here. So whatever 27 minus 13 is, which is 14, that's going to be our number of neutrons. How do I get this? I have a 3 positive charge. That means when I add up my protons and electrons, there must be a difference in the favor of positive by 3, right? So in order to do that, I can't change my number of protons. How many do I have? 13. If I'm going to have 3 more positive charges than I am negative charges, then how many electrons must I have? 10. Okay? That's why I have 10 electrons there. Okay, good. It says mass number is not the same as the atomic mass. There's a subtle difference. Make sure you understand. The mass number comes from adding together the protons and the neutrons. That's what the mass number is. It's individual to your atom. Okay? The atomic mass is when we incorporate all the possible isotopes and take that average. Okay? That's the only difference. You can see how they're very closely related, but they're subtly different. One has to do with your individual atom, add up your protons and neutrons, there you go, atomic mass number. Atomic mass is going to be everything all-inclusive, including all of your averages for the isotopes. So they may not work out exactly the same. If you have chlorine-35 and you have 17 protons and 18 neutrons, that mass number is different than for chlorine-37. But if you look up chlorine in general on the periodic table, you'll see the atomic mass is 35.45 because it's already figured in all of that stuff. Okay. So here's our final problem here. Back to gallium. Remember I said gallium is the one that can actually melt in your hand. You can get it to 29 degrees Celsius. Gallium has 2 naturally occurring isotopes. There's gallium-69 with a mass of 68.9256 AMU. Its natural abundance is 60.11%. Okay? So most of all the gallium that's out there is gallium-69. Gallium-71 also exists. Its mass is 70.9247, has a natural abundance of a little bit less, almost 40%, 39.89%. I want you to actually calculate the atomic mass of gallium. Now your table obviously tells you the atomic mass of gallium. So when I ask you this on the exam, how to calculate this, you just can't look at your table and write down the number. You're not going to get any credit for that. You have to show me how you got this number and prove to me that you know how the periodic table came up with this number. Okay? So I want to know the actual atomic mass that you see written there for gallium. I want you to calculate that based upon this data, just like the people who designed this table would have. So what you want to do is realize you want to find, okay, I have this much percent that weighs this much, and I have this much percent that weighs this much, and for every different type that you have, you do the same thing, and then you're going to add them all together. So if I have 60% that weighs this much, I take 60% times that. If I have 40% that weighs this much, I take 40% times that, and then I add all of that together whenever I'm done. It's really not that difficult. So the first thing you want to do is just like when you're doing math and you're dealing with percents, in order to type this in your calculator and do the math, you're going to want to convert to a decimal. So you should know, hopefully by this stage, that 60.11% is 0.6011. Okay? If you struggle with that, you need to see me, okay? Because we've got some math issues we need to deal with in order for you to succeed in this course. All right, so gallium-69 would be, the percentage abundance would be that. For 71, it would be that converted to a decimal, which is that. What we're going to want to do is a formula that looks sort of like this. We want to take the percentage of abundance of whatever one we're dealing with first, let's say gallium-69. We'll take whatever percentage abundance that is, which would be this, times the mass of whatever that is. I tell you up here, the mass is 68.9256. Okay? You put that in there. Then you're going to want to add all your isotopes together. So you'll add, do the same thing. What is your percentage abundance of the next one? Times its mass. Percentage abundance would be 0.3989, and its mass would be 70.9247. It's that simple. Do those two steps for every isotope that you have and add them all together, and you should get the number that you see on the periodic table. So there we go. Plug and chug. Plug in your numbers, chug out an answer there. You should get 69.72. Does that agree with gallium? All right. So there you go. Questions? You know everything?